So
yeah, you're always removing it.
yeah, I wasn't too sure what to talk about, and then I listened to a bunch of people. I spied on a bunch of the groups. I talked to some people, and there was a common theme. So this might actually end up being a useful talk. So it's about representing syntax in Acta or in any dependent type language. Why would you want to do that? Because you're mathematicians, you don't care about syntax maybe, and you want to prove your theorems on your actual objects. Well, you could want to implement your own system maybe, because the existing ones don't internalize the kind of logic you want to study. I heard someone saying that they wanted to represent the lambda calculus with explicit substitution, so you'll need to first get it in the system. That's something you need to do. You may too want to prove meta results about your theory. So I have a colleague in Strathclyde called Bob Atke, who is this really neat little language based on linear logic, and internally you can prove, no, externally at the meta level, because you have this deep representation of the theory, you can prove that all the functions from list to list are permutations. So you can implement a sorting algorithm which you know will preserve all of the values in the input list and put them somewhere in the output list. You may want to represent semi-decidable formulas in your theory so that you can write a solver for it. So an instance of that would be Presburger arithmetic, and then you have quantifiers, so you have binding and you have all sorts of issues. Or you could want to work in the internal language of a category rather than manipulating the object directly. So I'm going to start from an empty buffer, and then we'll see how far we can get. When should I stop? By the way, is it 11 or half past?
No. 35, I think, would be the correct answer.
Okay. Well, we'll see how far we get. So I'm just using this magic interleave mutual for the moment, but it doesn't matter very much. It's more for pedagogical purposes than a very technical aspect. So the first thing I'm going to do, I'm going to define a type of terms. And so that's just an inductive type, which in Agda is called set. It's not called type for some reason. And then I'm going to introduce the first constructor, say a literal. So I'm always using backticks to denote syntactic objects because we are working both with the syntax and then we'll talk about the semantics, so also the object in the host language. So not to mix them. So it takes a natural number and it gives you a term. And then we can decide to write an evaluation function for it. So let me just say, okay, this is going to be my signatures, and then here I'm actually going to start throwing constructors and cases in. So this is what the interleave mutual allows you to do, just to separate the declarations from the implementation. So if I write an evaluation function, well, so far I only have literals in my language, so I can just say, okay, everything will evaluate to a natural number. Okay, I'm missing a value here, so I can say, well, let's look at t. So we have this interactive mode, of course. There's only one possible case. It's the literal that I first introduced, and I can just return it. And so I have this amazing language with only literals, and evaluating it just returns the literal directly. So let's just say then we can decide to, I don't know, throw in a function, for instance. So I'm going to add a new constant called plus. Maybe I should do this a bit higher in the buffer. And this time it takes two terms and returns a term. And I need to explain how to evaluate this function. Oops. Emacs issues. So I do this by case splitting on the term. Agda generates horrible names for them. And then I will just map as to its meaning, and then use the built-in like addition function for natural numbers to give the meaning to plus. Okay, so now I actually have syntax trees, right, that are plus nodes, and then eventually at the leaves you have some literals, and the evaluation will just compute away the full string. So to make it a bit more interesting, maybe I want to have variables in that language too. So this is the very, the simplest language you can have, where you start having open terms, and so you can talk about optimizations and this sort of things. So I'll go into here, and then I will need to add a case to the variable, to the evaluator. And of course here there is some freedom in how you decide to represent variables. So you could use strings, and then to give a meaning to the terms, you would need a partial map with finite support from strings to values to be able to interpret all of the variables. But talking about partial maps and finite supports, what does it even mean to be finite in a constructive setting? There are many different ways to specify that. We probably want to avoid that. So instead, we're going to define the notion of scope at the top. So it's a set, and then the terms will come indexed by a scope, telling us what is in the context. And then for evaluation, we will have some notion of environment that I'm going to need to throw in also. So an environment is something that takes a scope and gives us a set. So these will be the interpretation of the variables in the scope, so the values associated to them. And then the evaluation function will be modified so that it takes an environment that appropriately maps variables to values. Of course, right, so I had to declare this variable construct to say that all of the gammas that are seemingly unbound actually refer to a scope, and so please generalize over it. Like, I don't want to be explicitly writing full gamma everywhere. It's equivalent to that, but this way I don't need to modify everything. And so, of course, now I need to revisit all of my definitions, because now the syntax of terms is now a family that's indexed by the scope. So literals are valid in any scope whatsoever, so we can just be universal. A plus node will be valid in scope gamma if its subterms are valid in scope gamma. Right, so we're doing live refactoring, so we're going from one error to the next. Eval is now taking this extra argument, environment, that gives a meaning to the scope. So all of the clauses that I had before, where I was just matching directly on the term, are not valid anymore. I need to introduce the environment, even if I'm ignoring it. So I like to call it row, and here it's row. I need to pass one in the recursive calls also, right? So here there's not much choice actually. So if we look at the goal, we can see that I haven't said what an environment was yet, or what a scope was even, but I can see that I have a scope in scope.
Scope, not in scope.
And then I have an environment for that scope. It just means that I haven't named it, right? If I bring it in scope, then it will show up here. So I haven't, if you don't write the name in the source file, then it is there, but as a user you cannot utter it. It's just a machine, like internal name. So that's why it's saying, because things are indexed by it, Agda needs to show you that this thing is in there somewhere, but because you haven't written it down, there's no way for you to mention it explicitly.
Well, why can't you refer to gamma here? Like, I mean, it's available, right?
Well,
On argument.
yeah, it's a generated name, so bad practice to mention
Well, I mean, it's gamma, you wrote it down, right?
But it could be refined by some of the pattern matches, right? So until you've type checked the clause, you don't know that it is gamma, or maybe gamma could be an alias for.
But why don't you need to do this with the TM data type? I would expect there to be an implicit gamma as well.
Yeah, so there is, but I declared this variable
Yeah,
here.
but why doesn't that work for default? I mean, what is the difference between data and function declarations in that respect?
Yeah, so variables are implicitly bound automatically, but only in types.
Okay.
But there's an issue on the tracker, and I would like it to
I
also
think
by
that's our
using
question.
the.
I was just repeating.
Right, but because it's the same scope being used in both of the subterms, we can just use the same. Oh, okay, it's not even able to find it. The same environment to make sense of the variables that are somewhere in the subterm. And then here, okay, so here now we need a notion of variables. So we need to finally decide what our scope should be. So a possible solution, we only have nats around, is to use a natural number. But this is going to be a pretty bad idea, actually. Why is that? Because when you have results in a given scope, sometimes you want to embed them in the larger one, right? You want to weaken your result so that you can reuse it somewhere else. And there's nothing that looks more like a natural number than a different one. So let's see. Yeah, I can write a test. I can say, oh, of course. So what this is saying is that if you use natural numbers to represent your notion of scopes, because natural addition on natural number, which is the way to extend an existing scope with extra variable, is commutative, it will be really hard to distinguish when you're adding variables at the back or at the front. So when you're writing something like, okay, let's see, a function from, I don't have a lot of types in here, so that just postulates that we have a var that's indexed by nat and telling you what it means to be a variable. If you try to write the weakening from var2 to var5, it's not at all clear where the three extra variables should go. Should they go at the front? Should they go at the back? Should they be interleaved? It's not clear from the type what should happen. So what we typically do then in this case is to, is it a built-in? I wonder, I can't remember. Oh yeah. We use lists instead because append on list is not actually commutative. Although, maybe I should define my own lists. I'm going to define my own list because lists grow on the left, but in inference rules, the context tend to go on the right. And so it's always confusing to reason backwards all the time. So we tend to prefer to have these kinds of lists. So I can have the empty scope, or I can have a scope that's extended by something on the right. And for now, we don't really care what it is. It could be names. In the implementation of Idris, for instance, internally all of our date types are indexed by the scopes. All of our language intermediate representations are indexed by the scope, which helps, like, say, prevent a lot of mistakes when manipulating variables. And in there, we are just using names because it's too hard to have anything more precise than that.
Shouldn't this be in a different section?
Sorry?
Shouldn't it be in the constructors and cases part? Because it says data. Oh, no. Okay.
Oh, I see what you mean. Yeah, I was thinking more the constructors of the language rather than the, yeah.
This is just.
So I guess I can, yeah.
I mean.
Good.
So this is a syntactic scope.
Yeah.
I mean, if we're being real, context is a snob list of types, so that will be mutual with the other definitions and therefore belongs in the signatures.
Yeah, so in this example, we're not going to be dependent, but eventually you may want to do that. It might be a bit tricky. And then I guess I can move my environment also to infrastructure. And this time I'm going to define it as something like this. Right, so now I didn't want to write for all, but this is the way we're going to do it. Right, so here I'm using overloading because essentially environments, if you think about it, they're just tabulating what it means to be a value for each of the elements in the scope. So why come up with new names when you could reuse the old ones? So this is saying that if we have an empty scope, then we can just have an empty environment for it. And this is saying if we want to build an environment for a scope gamma extended with something sigma, we don't know, we haven't specified what it should be yet, then we just demand a value for that bound variable called sigma. And so far the value are just natural numbers, so I just asked for a natural number.
What are these values supposed to represent?
So they're the values of the terms in our language.
So that should be like some kind of type that holds every value, or like?
Yeah, so far our notion of value is
Like an evaluated terms.
yeah, it's just we only have literal numbers and false, so it's only going to be natural numbers. Right, so to build an environment for gamma extended with sigma, we need an environment for gamma, and then we need a value for sigma, which I've written not here. I suppose I could write it slightly differently, but yeah, let's just bite the bullet. Let's just, well, we don't know what this is, but so far I just constant maths. Okay. And so now we can finally, well, not yet. So now we have scopes that are left nested lists of bindings. We don't know what they are yet. So what it means for a variable to be in scope just means that we have a path from the local end to where it was bound. So this is just the bounding. So let's see, where should I put it? Bound. So it's a scope to set. Or actually it's a something to scope to set. And we have two cases. So either we have the Brown index 0, which means that we have found sigma in the context, in the scope that was gamma extended with sigma. It's at the local end, so it's the most local variable. Or we have a successor telling us that if we can find the variable somewhere in gamma, then we can find it in gamma, where the most local variable is anything, so I just called it in this instance. Okay. So now here we can say that a variable is represented by a strongly typed de Bruijn index that tells you where in gamma you originated. And so when you're writing the evaluation function now, you can actually spec okay. Right, so for now, let's just put dummy values in there. And we should be able to split on it. So we have no information whatsoever about the binding sites at the moment, so they're just not bothered. So if we have the variable 0, corresponding to the De Bruijn index 0, then we know that necessarily the scope is non-empty. And so necessarily the environment will have a value for the most local binding. So we can split on it, and this will give us the value v that we can return immediately. And we don't need to consider the case var 0, because it's just impossible. So maybe I can write it this way. Well, it needs to be below. It's already covered.
It's epsilon. Yeah, anyway.
Yeah, it's saying that there's a valid pattern.
So you could
here,
put
which is
epsilon
the-
there.
Right.
And then you could put open parens at the end of it.
Oh, but that would still be valid, right?
Yeah. No,
Oh, do you
just
mean this
epsilon,
one?
just epsilon, that's the whole thing.
Yeah, something like
And
that.
then you could put absurd case.
Yeah. Yeah, so I didn't need to write the case in the first place because I was smart enough to detect it, but basically the idea is that if you look at this definition, all of the return indices mention the constructor comma, which is this extension of the scope with a new binding. And so therefore, if you know that you have a proof that you have a De Bruijn index in scope, you cannot possibly consider the empty case.
It's a GADT.
Okay, so, and then if you have a successor, similar thing, the environment should be non-empty. And now this is where I'm wondering whether determination checker is going to shout at me, probably not. And so, because you're not considering the most local function, you can just drop the associated value and then evaluate the variable in the restricted environment. Okay. So far, so good. Right? Yeah.
Why do you distinguish between the environment and the Bruijn? I mean, is there a more complicated type than units that you would put in some more advanced applications? I mean, for me, environment and the Bruijn basically are just a fin type, but maybe I misunderstand what's going on.
Right, so where will we?
You don't really
Environment is isomorphic to the type now.
You don't need that top there.
Fine.
It's not serving a purpose because the grind indices are just locations, right?
Yeah,
They don't carry information.
so far, yeah.
So scopes are natural numbers, and De Bruijn indices are fine at
Yeah.
scope.
Okay.
Yeah, so
So what would be better than, what would be in the place of units in a more advanced?
So suppose you had function types. If you had function
Yeah.
types, like not just a unit type system of natural numbers, you want to know whether the variable has type not to not or something else, right? So a context would be a list of types annotating the variables.
Okay.
So this is exactly what I was going to suggest we do, or rather something not as hard, maybe, for now. So we can add a new pair constructor, and a pair takes two subterms, just like plus, and gives you a term in the same context. And then we can write the evaluation function. So if we have an environment, and a term, we can split on it. We have a first and second projection, but now the way we define the evaluation function means that we need to return a natural number. The whole point of this pair was to actually return a pair of values. So now we need to actually go back up and start patching our definitions to account for this extra complexity. So the first thing to do is to introduce the notion of types. Oh, actually, I don't need to define them quite yet. And then the scopes now will be storing the types of the variables, which means that the de Bruijn indices, now this is a scope, so this is a type, so this cannot be unit anymore, and this needs to be a type. And I actually have a handle on this now, so I can store. I want sigma and tau to be referring to types, and so now I can just remove this nonsense here.
Call them capital A and B.
And here, the notion of value will now depend on the type. So maybe this is yet to be defined, or should I define it right now? Maybe I should. So now that I have pairs, I'm going to need a semantic notion of pair to make sense of them in the evaluator. So I'm bringing more built-ins.
You haven't defined tie yet.
Maybe I can wait a bit. Ooh, I know. This is the beauty of the mutual. We can just declare stuff and define it later. So here I have already said that I wanted to have a value for whatever sigma was. Sigma was unit at the time, but now it's something interesting. I still have, so far, the same definitions. And then here I have my first type, so I can say, okay, I want the type of natural numbers. So again, I'm using backticks to differentiate between the meta level and the object level. Okay, plus works, the browns, and now here we see that we're facing a problem. So the variable, let's just comment this out. The issue with refactoring, we try to make as many errors into warnings as possible so that the file stays interactive as much as possible, but sometimes when you have hard type errors, you're still forced to comment out part of the file to keep interacting. This is the way it is. So with the variables, we can see that now we have this notion of the Brown index telling us that we found the type sigma somewhere in the scope, and then we are still only saying that we're building a term in scope gamma. But we would need to somehow keep track of the type of the thing we're constructing here. So this leads us to revising the definition of terms. We go back up. And the term is not just indexed by a scope anymore, it's also telling you what it is that you're proving. So it is also taking a type now, which means that the evaluation needs to change. So now it takes a term of gamma sigma, okay. The literal takes a natural number and gives you a term for a natural number, plus, well, the two subtrees better be for natural numbers if we're going to add the results together. And finally here in the variable case we have exactly the variable, the type of the variable we just looked up. Okay, let's try to make some progress. So this code for the variable case in the evaluation function is still rejected because we didn't quite patch the type of the evaluation function. If we go back up, we see that we're saying if we have an environment for gamma and we have a term for with three variables in gamma and producing like being a proof of the type sigma, then we still return a nat no matter what. But the environment gamma is giving to variable of type sigma an interpretation as value of type sigma, and not just natural numbers. So here it's a matter of saying that we're actually going to return a value of the appropriate type. Okay, so let me just scroll back up. Right, so I'm saying now, if I know how to make sense of gamma, then I will know how to make sense of sigma, because the term will tell me what computation to perform. And of course, every time I reload, it jumps to the next
Because you
pair.
haven't defined val.
Exactly. So we haven't defined val, but we just gave a constructor for tie, so we can define what it means to interpret sigma here. And of course, values of type nuts are actual object value natural numbers. Okay, so going back to the pairs, we can throw in a new type constructor for pairs that takes two types and returns a type. The value will be left defined. And the pair type takes a subterm of type sigma, a subterm of type tau, and gives you a term of type pair sigma tau. So this is the usual constructor for pairing. And now here what we would like to write is the pairing of the evaluation of rho and t. And we can actually do that. Okay.
Because you haven't given a case for pairs and val.
Yeah, but this is not the most helpful, right? I was hoping that the inference would tell me that this was a product of values, but they just decided to leave the meta variable. Or maybe if I normalize it? No. Okay. So then we will add the new, the meaning of the pair type as the pairing of the meanings of the two types. And now, if we look at this,
Do you think it would be less confusing if you use the cross instead of the sigma there?
Yeah.
yeah, it's in the standard library, but it's not in the built-in file. And, I guess I could import the product.
The inference might work now. Oh, because it's dependent. You can't infer it in general because it could be a dependent type. It doesn't have to be constants. It just evaluates that. So,
I don't know, like the type of S is
but it could be a dependent
known,
sigma.
right? So we have everything could be reconstructed.
But it could be a permanent dependent sigma. It's
Oh,
yeah. So the second type, it does have to be a sigma constant type.
Let's see if this gets better. So in the standard library, we have this convention of using a prime to mean the non-dependent version. Right. So that gives us pair, and then 5 minutes to do functions. Sure. So it's the same. We have a new type constructor that takes two type and returns one. We need to define the new notion of value, and we need to throw in some new term constructs. Maybe I can do the let's make it. So the new type of value will be, as you might expect, functions from values to values. And then the new term constructs will be lam. So this is, oops. So this is saying that if you want to build a term of type sigma arrow tau in context gamma, it's the same as just building a term of type tau in the extended context. So you just call the variable at the local end of the context. And then application allows you to given a function and its arguments, apply the function to the argument and get, I mean, this is essentially the type of modus ponens, right? And then evaluation, we will not have the time to write it, I suspect. So let's cheat and do the easy case first. Oop. So here we are applying a function to its argument. Well, we may just remember that the notion of value for functions is exactly function between values, functions between values. So if we evaluate row F, we normalize it, we see that we get a function from a horribly named domain to a value in the codomain, and we want a value in the codomain, so we can just refine by that. Okay, got rid of the parens, but I'm going to put them back in. And then here we can evaluate the arguments. And here we remembering that, so lambda constructs a function, therefore we need to return a value of the function type, which normalizes to a function between values, which means that you can grab whatever argument is going to get passed to that function in the future, and now we need to come up with a recursive call that will evaluate the body of the term. Almost there. So we are going to evaluate the body. So we need to provide an environment for gamma extended with sigma. Well, we have a constructor for that. It's the same one. On the local end, we need to provide a value for the newly bound variable, sigma. So we can just pass v. And on the other side, we need to provide an environment for the values for the variables that were already there. And this is exactly the environment that we have. Right, so this is just a quick way to show you some of the good practices when you are embedding a language in ACTA. So not using natural numbers to represent scopes, because this gets you confused about where the variables are flowing. Using this kind of well-scoped de Bruijn indices. Of course, if your type system is too complex to actually fit in the language, you can still use top everywhere and not have the types enforced in the syntax, but you can still have these constructs here like de Bruijn. And then for the evaluation function, this was just embedding the language directly into ACTA. But if you want to actually use it to normalize your terms, you will need a little bit more structure to come back from the evaluated value and extract some syntax from it. And this is basically a model construction using presheaves. So if you know how to do this in category theory, maybe you can have a look at it and try to do it in ACTA to actually implement a partial evaluation function.